All right. We're ready. Let's do what we do. Hypothesis testing. All right. So quick recap. And then what I want to do is just jump right into an example and just kind of show you the ropes using the example. Okay. But just as a quick review, because it's been, I guess, a weekend and a bit, right? I think, yeah. I don't know. Time flies when it's March. I don't know. Can't stop it. So we started and introduced just the steps for hypothesis testing. The first step is to state your hypotheses. Okay. State the hypotheses. And there were some rules that we established last day that we're just going to jump right into. You've got your null hypothesis, colon, and your hypotheses have to be about the parameter, right? And so for this case, we've only started with one sample proportion type question. So it's really hard for us to establish what type of question we have until we've seen other types of questions. But for now, one sample proportion questions, I'll put that here. One sample proportion types, or type, I guess. That's the only type of question we've introduced so far, okay? But if it's one sample proportion, which means that you have just one sample and you want to analyze a proportion from that sample, okay, then you're going to have P is equal to some hypothesized proportion P naught. Okay? And then the alternative hypothesis is going to be that P is not equal to P naught, right? Or less than or greater than. What we said was if you're unsure, then use the not equal to, right? It's going to be the safest thing. Okay? And even if you are writing a research paper or something like that, then usually we use it to, so then we use the not equal to anyways, right? And so step 2, thanks, Joy, is to do the test, right? And so I call it do the test, but really what I mean is calculate the test statistic, but that doesn't have the same ring to it. Calculate the test statistic for one sample proportion. That test statistic is a Z. How far is P hat? So your sample proportion, how far is it from P naught with a spread of P naught Q naught over N? What I think I didn't get to last day is point you towards the formula sheet. It's probably down here somewhere. And show you that if you've decided, and maybe I'll go back to the formula sheet and just kind of scribble on it to bump it to the top, then erase it. Okay. So if you've decided that you have a one sample proportion type of question, right? So first thing you're going to read and say, okay, what type of question do I have? That's the most important thing, I think, right? And then you'll have one sample proportion to choose from and then just kind of scanning ahead. Or if you have two sample proportions that you want to compare, or maybe you have more than one proportion, right? More than two proportions, more than two proportions. Maybe you have one sample mean, right? So we're going to work through these just throughout the chapters, okay? But for now, this is the only type that we have, okay? But what I've done is I've given you the sampling distribution for each type of question. okay? I gave you the formula for the confidence interval for P, which we did last week. And then for the hypothesis test, okay, I give you the default, null, and alternative hypotheses, right? And then I also give you the test statistic. So basically I give you step 1 and step 2. After that, right, you need to know how to use a Z to find the area in the tail, which is the p-value, okay? And then use that p-value to draw your conclusion, right? So here I hold your hand through step 1 and 2, and then I let you swim on your own. No, push you in, sink or swim, no. And then later today, hopefully, I'll just show you how to calculate a sample size that you would need in order to achieve some desired margin of error, okay? And that's the only time that we do it is in one sample proportion. It's just for practice. Okay? So here, right, what I want to do is I want to bring in and just show you that here I give you step 1. You still have to read from the question, right? Figure out what P naught is, right? That's going to be some number. Okay, so here, this is step 1. Oops, not period there. And this is step 2. All right, calculate the test statistic. Then step 3 is find the p-value. Yeah. So what's going to happen is we have 3 different scenarios, and they all track back to the alternative hypothesis. Now, I didn't draw these out last day, so this is kind of new, not really part of the review, but sort of, I don't know, it's all one big happy family, okay? But find the p-value depends on the alternative hypothesis. So notice here, this is HA, okay? If HA says that P is not equal to P naught, what's gonna happen is, okay, well, we said this distribution is actually centered on P naught, okay? Because it's what we think the center of the distribution is. So that's what we hypothesize. Then what's gonna happen, and this is kind of the tricky part, and probably why I shouldn't have started with the not equal to, you'll see why, but it's the most common, so that's why I wanted to start there. Your p hat, so your sample proportion, is only going to happen in one of these tails, right? So on one side. But what happens is we say, well, it could have just as well happened on the other side, right? So if, for example, p hat was up here, then we say, okay, well, what if I just replicate it and make it happen on the other end as well, right? And so then, right, this area here is the one-sided p-value. But what we need is actually the two-sided p-value, which is this area. And we kind of force it to happen down here. So the two-sided p-value is the one-sided p-value times 2. Right? You just pretend that it could have just as well happened on the other side as well. Same thing, right? If your sample proportion is below the hypothesized proportion, then you would pretend that it could have just as well happened just as far away on the upper side. And then the p-value, remember, is the probability of seeing something as extreme or more extreme, which means that's why it's the area in the tails. Okay. So this is the trickiest one, I think, the two-sided p-value, right? And it's because we have a two-sided test. Okay. Now, if you have the other two options, right? And let me see if I can squeeze these in here. Are that HA is P is less than P naught. Yeah. What would that have to look like? Well, P naught is still at the center for both of these. P naught, and HA is P is greater than P naught. If your hypothesis is that P must be less than P naught, your sample proportion must be less than P naught, right? You can't use 0.8 to prove that it's significantly less than 0.5. That just doesn't make sense, right? There are kind of some examples where people have done that, right? And used something larger to prove that it's less than. Doesn't work because your p-value would be huge, right? So just something to be careful of. And I'm pretty sure in the assignment, it's not posted yet, but I'm pretty sure in the assignment, there is an example where you have them switched around and you have to pay attention to that. Okay. But if P is less than P naught is your hypothesis, then your P hat should be less than. And then this area is the one-sided p-value. So that's your p-value. Okay. Using the table, we're going to have a range, right? Somewhere between 0.01 and 0.02 or something like that, right? And same thing on the upper end. If your hypothesis is that P is actually greater than P naught, then of course your P hat, your sample proportion should support that and be on the upper side. So depending on how your alternative hypothesis is set up, that's going to determine how to calculate your p-value in step 3, right? And so that's hard for a lot of people so they don't know, how do I know if it's a 1 or 2-sided p-value? Well, you have to go all the way back to step 1 and figure out what your hypothesis was, right? Okay, nice. Of course, on your table, if we go to your table here, it's already done the work for you, right? So if you want a one-sided p-value, right, then the range is going to be somewhere on this first or second line, okay? And if you have a two-sided test, then you use the two-sided p, right? And so it's already done that work of multiplying by 2 for you, right? 0.25 times 2 is 0.5, 0.20 times 0.2 is 0.4, right? So it's already done that, kind of redundant, but it's just nice to have, right? And so here, these guys go to this line, and these guys go to this line. Okay. And then, of course, you can use software to find the actual values, right? But using the table and on the quiz, and on the final exam, right, you'll just have to give me a range for the values. Okay. But using that range, you'll be able to do step 4, which is your conclusion. You know what? I'm going to bump it to a fresh page here. Wait, maybe not that far. First, you have to compare the p-value to the alpha level, right? The alpha level is the significance level, and as a default, we use 0.05. Okay, so that's a lot, right? And so if the p-value, and maybe I'll parking lot this for a bit here and just do the steps. So compare the p-value to the alpha level. Oh, I don't know where that went. It's gone forever. If the p-value is less than the alpha level, which is the significance level, which has a default. So if it doesn't say default alpha is 0.05, And it is linked to the default confidence interval of 95%, right? You're either 95% confident it's within this range, or there's a 5% chance that you're wrong, right? So they are linked, but that's beyond us for now. So then we need to state the conclusion in terms of the null hypothesis, right? So the conclusion in terms of H naught. And this is where people like to throw their own spin on things, and I don't want you to, right? And so I just want you to say, do you have enough evidence to reject H naught or no? Okay, so the conclusion in terms of H naught, so following from here, if the p-value is less than the alpha level, we have enough evidence to reject H naught in favor of HA, right? You either do have enough evidence or you do not have enough evidence to reject H naught, right? And so the flip side of this would be if the p-value is not or not less than the alpha level, we do not have, oops, sorry, I put it in the wrong space. We do not have enough evidence to reject H naught. And then you wouldn't say in favor of HA because you're not rejecting it. Okay. So those are your only two options, right? Depends on how the p-value compares to the alpha level. Then the conclusion in terms of, so what does rejecting H naught mean in terms of the question? Conclusion in terms of H naught. Right. So what does rejecting or failing to reject H naught mean in terms of the question? This is where you rephrase the question as an answer. Based on your conclusion. Okay. So it's all very formal and it's meant to be that way. It has to be that way, right? And there are a lot of things to keep in mind. But once you've done enough of them, then, you know, they're long, but they're not hard. Okay. Okay. This, and I should have grabbed this earlier. Where is it? Let me just find it. It's worth the wait, I promise. Wait. Wait. Hey, keep clicking on stuff accidentally. Okay, I promise. It's worth the wait. I like to use this one. To help you remember. If the P is low, then the null hypothesis must go, right? That's what it says. And this is just to help you remember, right? If the p-value is less than the alpha level is really what it's saying, then you have enough evidence to reject H naught. But this one has a slightly catchier ring to it. And usually on the final exam, on a few of them, I'll see scribbled in the margins somewhere, if the P is low, then the null hypothesis must go, right? And they're like, okay, yeah, got it. So at least, although it's a little bit passe, it is really helpful though. So what does that mean? It means that visually, what's gonna happen is there's some region here, and let's focus on the two-sided test because that's your default, right? There's some area here, 95%, right? So if it's within that 95%, that central 95%, right? Then this here is the region where you do not have enough evidence to reject H0. It's hanging around, so as long as your p hat is somewhere in this range, right, then you don't have enough evidence to reject H0, right? P could be P0, could be something else, right? It's not necessarily P0, but it's not significantly different from P0. Okay? So it's basically, I like to think of it as, okay, so here I'm sitting at the table, even though I'm not completely up against the table, right? And I'm allowed to lean back a little bit further, but at some point, right, if I'm over here, you would say, well, actually you're sitting by the whiteboard, you're not sitting by the table anymore, right? So there's this wiggle room, and we've decided as a field that 95% is within reason. And then anything else, so once you move out into the tails, this is your rejection region. Where you have enough evidence to reject H0. Okay. So that's what it looks like. Okay, so once you moved out into the tails, but then we quantify that with the p-value, right? Because the probability of it being P0, of the center being P0 is so low, then I can reject it. Okay, let's jump into that example. Throw you right in. 5.22 is what I wanted. And, oh, not example, it's exercise. For some reason, all the exercises I choose are about sleep. I realized kind of way too late. Usually I just pick ones that are short and easy to read. Notice how this one's the shortest. All right, so, well, I guess I ended my review. Let's say I ended it here, although it kind of ended a long time ago. All right. Jump right into an example. 400 students were randomly sampled from a large university. And I'm just now realizing I haven't talked about the conditions, but I'll introduce those here. And 289, they did not get enough sleep. Conduct a hypothesis test to check whether this represents a statistically significant difference from 50% and use a significance level of 0.01. Okay. Fair enough. So a couple of things. I've got my sample size, right? And I've got some number of that sample size that said that they did not get enough sleep, which seems to be what I'm interested in here, right? Conduct a hypothesis test to check whether this represents a statistically significant difference from 50%. And so here, how do we denote successes? X is 289, and maybe I should, N is 400. I want to know if there's a difference from 50%. Okay. This tells me what my alternative hypothesis should be, right? I want to know if there's, so I want to know if P is not equal to, right? Is it different from 50%? I don't care if it's less than or greater than, right? I just want to know if there's a difference from 0.5, right? Because it has to be a proportion. So usually we deal in percentages, but for math, we use the proportion. Okay. So that told us our alternative hypothesis right away, which means, so therefore P naught is 0.5. What we haven't talked about yet, and this, it's time to, oh, I guess there's one last thing that I should say here. It says to let alpha be 0.01, right, instead of the default 0.05. Okay. This is what's new, which we haven't talked about, is the conditions for a hypothesis test for proportions. It's very similar to the conditions that we've seen before, which are what? Independence. If the sample was randomly selected, then you can assume independence, right? And then the success failure condition. The success failure condition is going to change a little bit because now we have P naught. So we do have some hypothesized population proportion. And so that's the only change. The conditions for HT hypothesis testing. So I use CI for confidence intervals and HT for hypothesis testing. I'll say it here though. So the first one, and I'll start it on a fresh page here. Independence. Is our first condition. Now the sample was, it says it was randomly sampled from a large university, right? And so students were randomly sampled, so we can assume independence. Students were randomly sampled. So we can assume independence. This, let's make a note here, same as confidence intervals. That condition is always going to be a condition for us, right? Regardless of the question type, we always have to assume independence. The second one is the success failure condition, right? I have to have at least 10 successes and at least 10 failures. We've seen that many times before already. But now it has to be the expected number of successes and the expected number of failures. Okay, so the change is that it's now about P naught, right? Whereas before it was the observed number of successes and the observed number of failures. Right? So that's the only change. So here, this has to be greater than or equal to 10. So the expected number of successes greater than or equal to 10. And N also has to be greater than or equal to 10, which is the expected number of failures. It's greater than or equal to 10. Again, this will always be satisfied. It's just we have to check it. So this part is what's new, right? It used to be P hat and Q hat, but now the change is that, okay, I actually have a hypothesized value for P, so I'm going to use that instead. But that's the change. And we saw that change in the standard error as well, right? We didn't use P hat and Q hat, we used P naught, Q naught, as we saw on our formula sheet, but we haven't actually done it yet. So now we're ready to say that therefore the conditions for inference are satisfied. Very generic. But you can always seal the deal with that. So now we're allowed to do our full hypothesis test. Now, luckily, we were able to pick out the alternative hypothesis right from the question, right? Which is always going to be the case. The question will give you the alternative hypothesis, right? And so step one, I guess you could, the conditions could be step one, but I don't know, call it step zero. You can't start unless you've checked the conditions. Step one, you're going to state the hypotheses. What's really nice is we already said the alternative hypothesis is that P is not equal to 0.5. Right? So we're going to have some sample proportion and we want to see, okay, is it significantly different from 0.5? So there's also going to be some number that you compare your sample proportion to, and that's the 0.5. What I like to do here is just make a note to myself that this is a two-sided test, right? Because of the not equal to, right? This helps me when I'm looking back and when I'm working on step 3. Oh shoot, what did I have? Oh, I have a two-sided test, which means I'm going to need a two-sided p-value. So this is where it's really important that as long as you follow through, right? So if you're unsure of what the sign should be, as long as you follow through and you use the p-value that's appropriate, then I'm happy, right? Okay. What's really nice is if you have your alternative hypothesis, then what's one of the first things we said is that the null hypothesis has to have an equal sign, right? It's going to have an equal sign, so you can start there. It has to be about the same parameter, and of course, how that parameter relates to the same number, 0.5. Okay. So notice that these guys, and this is the only change. Okay. Okay. Step 2, do the test, which is really calculate the test statistic, but it doesn't sound as fun. Z is p hat minus p naught over the square root of p naught q naught over n. And that's from your formula sheet. Let's see here. Just bring that in. It's a little small on there, but it's okay. So what are we doing? We're just figuring out, okay, well, relative to the spread, right, which we would expect with P naught, right, how far is P hat from P naught? So Z in our case, well, we need P hat. We haven't calculated P hat. And you know what? Maybe I'll do that here in this tiny little space, right? Because why not? P hat is X over N. And it's very, very painful, but I am going to work across the page because obviously I've already written stuff. But 289 over 400, which I have somewhere here. What do I have? .7225. Does anyone? Can't tell if that's been rounded already. 289 divided by 400. Okay, so that is the value. So I'm going to use that whole thing because it's only 4 decimal places. Why not? So that is the value. Phew. So I have P hat, I have P naught. Now that's all I need, right? I have N. Q naught is 1 minus P naught, right? So we're ready to rock and roll here. 0.7225. How far is it from 0.5? When the spread is 0.5 times 1 minus 0.5 divided by N, which is 400. In my notes here, I have 0.2225 divided by 0.025, but I'm just going to confirm that. 0.5 times 0.5 divided by 400, then take the square root. You don't want to forget that square root. It is 0.025. This 0.2225 divided by 0.025 is a huge Z of 8.90. It's just 8.9. But the table gives it to 3 decimal places, right? So you just want to assure yourself that it's 3 decimal places. That's a huge Z, right? That means that our sample proportion is 8.9 standard errors away from the hypothesized proportion, right? That's very far away, meaning it's very unlikely that this sample proportion came from a distribution that's centered on 0.5. It's more likely that it came from a distribution. Oh, yeah. Oh, sorry, that was scary. Yeah.
Sorry, I know. Sorry, I know. Could you just state that again? Could you just state that again? That the 225 is 225. What is?
Oh yeah, I'm gonna write it down.
0.5 is what?
Yeah, okay, I'm gonna write that down.
Okay, thank you so much. Thank you so much.
Yeah. What was I saying? Yeah. So 0.7225, right? It's unlikely that it came from a distribution centered on 0.5, right? Very unlikely, right? And so here, just as a note, since, and let's say, I'll give the numbers, P hat 0.7225 is 8.9 standard errors away from, and maybe I'll just bump it over here, from the hypothesized proportion of P naught equal to 0.5, right, is unlikely our sample proportion came from a distribution centered on 0.5. Our sample proportion from a distribution centered on 0.5. Right? It's more likely it came from a distribution not centered on 0.5, which is our alternative hypothesis. Right? It is more likely, and if this is not what you meant, Sammy, then speak now. It is more likely it came from a distribution that is not centered on 0.5, right? Which is the alternative hypothesis, is that P is not equal to 0.5. We don't know what it is. And because our alternative is actually just that it's not equal to, I'm not going to go into any detail about it being potentially bigger than 0.5 or anything like that. I just say that there's likely a difference, right? Something different than 0.5. Okay. So you don't have to write this part, right? But that's the logic, right? 8.9, a Z of 8.9 in our p-value, right, kind of makes a mess a little bit until we're used to it. And so step 3 is find the p-value. So I have this distribution and it's centered on 0.5, right? P naught is equal to 0.5. And then what happened? Somewhere way out here is P hat equal to 0.7225, which had a Z of 8.9. I want to find a range for these values. It's going to be very, very far out in the table, far out. But how do I start this? I'm going to, since the absolute value of Z equal to 8.900 is between two values from the table, right? Now those two values are going to be what? They're going to be from here, bring them in. And I'm going to bump this down and give myself the table first. Okay. So here on the Z star line, what I'm going to do is actually finish the table with Z of infinity, right? Just to kind of help myself out a little bit. Okay. At infinity, it's kind of weird if you think about it, but at infinity, the area in the tail past infinity is 0, right? But it's not until you reach infinity that it is 0. 0 times 2 is still 0, right? And so you can kind of finish off the table if it's helpful, right? Because now what are you going to say? Z of 8.9 is between 3.291 and infinity, right? So 3.291 and infinity. So what I'm going to say, because I want a two-sided p-value, right? And that's referring to my alternative hypothesis, right? Way back in step 1. So you can see how that's a huge disconnect for a lot of people, right? You get here and you go, okay, well, which one do I want here? And it's hard to remember, okay, I got to go back to step 1. What was my alternative? But that's why I make a little note to myself when I'm in the groove up here. Okay, I need a two-sided p-value, right? So I have a two-sided test, and so I need a two-sided p-value. So the two-sided p-value is going to be between two values. And just make sure you read them from right to left, right? Because you're going to have the smaller value attached to the larger Z. But as long as your interval makes sense from 0, it's somewhere between 0 and 0.001. Okay. So we don't know exactly what this p-value is, but we know it's going to be very, very, very small, right? Somewhere between 0 and 0.001, right? So now, okay, that's good. And then sometimes I get questions like, well, we're using a significance level of 0.01. What if 0.01 is part of the interval, right? Well, it's either going to be on the lower end, right? So between 0.01 and 0.02, or between 0.01 and 0.005. Either way, right, you can determine on which side the significance level is, right? And so even though it's a little bit weird, then you can still work with that interval, just thinking about where does the significance level lie. All right, so that's the p-value, right? Or you can use software, right? So step 4 is your conclusion. Can I squeeze it in on this one line? And I'm going to say, recall that alpha is 0.01 from the question. In fact, I'm going to snag the question, because what am I about to do? I'm going to reword the question as an answer in the end, right? That's our job, and that's the one that people forget most of the time, kind of ironically enough. They forget to tell me what the answer is. Because first, feels like you have to do a lot of work, right? First, you have to compare the p-value to the alpha level. In this case, right, the upper end, I usually just focus on the upper end, right, is 0.001, which is less than 0.01. So I'm just going to write that out in words, and that is part of your conclusion. So since the two-sided p-value is between 0 and 0.001, and I always use this format, right? I want to highlight that, yes, I have a two-sided p-value, which matches my two-sided test, right? You always want to showcase all the things that you know, right? And it's between 0 and 0.001. It is less than the alpha level of 0.01, which means we have enough evidence to reject H0, right? Because the p-value is so low, which matches that note that we made, right? A Z of 8.9 tells us, oh, okay, the null hypothesis is probably not applicable here, okay? So it all checks out. It's less than the alpha level of 0.01, which means we have enough evidence to reject H0 in favor of HA. This is one of those where rephrasing the question as an answer is not terribly easy. And I'm not looking for any sort of beautiful write-ups here or anything. So what I would say is, therefore, we have found that the proportion of students who do not get enough sleep is statistically significantly different from 50%. Kind of a weird one. On the quiz, I give you the question, and it's going to be easy to reword it as an answer, right? And so therefore, but in this case, it's a little bit harder. Therefore, we can say that, now what did I say? That the proportion of students, this is to mean all students, right? Because our conclusion is in terms of the population proportion. All students at this university but you can just say the proportion of students who did not get enough sleep or who do not get enough sleep is significantly different from 50%. I'll clean this up here. We did it. Whew. Kind of long, but kind of fun, maybe, sort of. I think so. Once you've kind of done, I'm like loving the nod back there. Yeah. Once you figure out the pattern and you see that it's always the same, then, I mean, for me, I always enjoy tedious things because then I know what I'm doing and I like knowing what I'm doing. And so we just need to get you to that point. All right. So let's see here. What I want to say is I find it helpful to think about the p-value because the p-value is kind of a weird thing, right? I think of the p-value as the probability that the null hypothesis is true. Now that's not 100% correct, but it's a helpful way of thinking about the p-value. Okay, and so just kind of another note, it can be helpful to think of the p-value as the probability that the null hypothesis is true. This is not 100% correct, but I do think it's a helpful way of thinking about it. So this is not 100% correct because statisticians are sticklers for these types of things. And so I don't want you to think that it's, but helpful as we learn about p-values. Right, so if you go back to what we just said, we had H0 is that P is equal to 0.5 and HA is that P is not equal to 0.5. And what we said was the p-value was between 0 and 0.001. If you were given these options and I told you, well, the probability that this is true is between 0 and 0.001, you would say, okay, well, I'm actually going to go for the alternative then, right? And so that's what we're doing, but in a more formalized way. Okay. What can go wrong? Let's talk about decision errors. So the p-value that we had in the previous example was between 0 and 0.001, right? And so we use that to reject H0 in favor of HA. But if we think of the p-value as being the probability that H0 is true, there's still a chance that we're wrong if we reject it, right? And so this is where decision errors come in. Okay? So decision errors when we conduct a hypothesis test, right? Regardless of what we did, right? We either reject H naught or we fail to reject H naught, okay? Which means we don't have enough evidence to reject H naught. So when we do either one of those two options, which are our only options, there's a chance that we're wrong, right? So there's always a decision error, but it depends on what our conclusion was. So when we conduct a hypothesis test and either reject H naught or fail to reject H naught, and usually we just write FTR, fail to reject H naught. There is always a probability that our conclusion is wrong. There is always a probability our conclusion is wrong. Okay. For that reason, I never, ever want to see you say you accept a hypothesis. Okay, so the word accept, I'll take marks off. I'll be super mean about it because you can never accept anything, right? Because there's between, in the previous case, even though it's very unlikely that H naught is true, right? You're not going to accept this just because there could be a chance that you're wrong, right? There's a 0 and 0.001 probability that you're wrong, right? And so for this reason, and I'm going to write it in red, for this reason, we never accept a hypothesis. Okay. The word accept is unacceptable. Ha ha ha. Okay, so I don't want to see you accepting any, you either have enough evidence to reject it or you do not, right? So those are your only options. Now, what I'm going to do is there are only two decision errors that I could make, right? I could reject H naught when I shouldn't, right? Or I could fail to reject H naught when it actually should have been rejected. So I think the best way to summarize this is in a table, because usually when I have to remember what it is, I kind of look at my mind table and then I can kind of figure it out. Okay, and so I'm going to steal it from the textbook. And where is it? Is it in this section? I think it might be in the other section. Oh, dang it. Figure 5.8 is the one I want. Huh. Okay. Okay. So I like to use this table and I kind of memorize it, I guess. Okay. So like we said, when we started talking about hypothesis testing, there is some population proportion. We don't know what it is, right? But it exists. We just, I don't know, we don't know what it is, right? And so here, there is some truth, right? And so either H naught is true or it's false, which means the alternative is true, right? And so here, what I want to make a note of is we will never know the truth about the population. The truth about the population. But that's okay, because we have the test conclusion. So this is our conclusion. I've decided that I'm not going to reject H naught. I don't have enough evidence to reject H naught. Okay. If H naught is true, then that's an okay conclusion, right? If H naught is not true, so if HA is true, I've made what we call a type 2 error. I guess I should have started with type 1 error. Okay. But a type 1 error is when I've rejected H naught when I shouldn't have. Okay. And so here, I'll just summarize these in words. But if I reject H naught and HA is true, then that's an okay conclusion, right? So a type 1 error is rejecting H naught when we shouldn't have. Okay. The significance level is the level that we're okay with making a type 1 error. Okay. So the significance level, let me write it in a different color here. The significance level, which is the alpha level, which we've decided a default 0.05, right? And then you can change it if you want to, but the question will either tell you or use a default of 0.05, but the significance level is the predetermined probability of making a type 1 error. Probability of making a type 1 error. Okay. So what we can do, if it's really important that you are not rejecting H naught when you should have, or sorry, that you, oh, how do I negate this? Logic. If it's super important that you're not rejecting H naught when it shouldn't be rejected, right? This drug is significantly better than the competitors. You don't want to say that. You don't say it, right? So what do? We say, okay, I'm going to really make it difficult to make a type 1 error, which means I'm going to lower the alpha level, right? And so maybe in another color, we can lower the alpha level. Looks like the alpha level in an attempt to avoid type 1 errors. A lot of our focus goes into type 1 errors, kind of avoiding type 1 errors. What's the probability of making a type 1 error, right? And so, but on the flip side, the type 2 error, and the reason it's not as kind of popular, type 1 error, type 2 error, is that there's really nothing that we can do about it. It's when we fail to reject H naught when it actually should be rejected. Usually the only reason we do that is because our sample size wasn't large enough to detect a difference, right? So then you'd have to increase your sample size, which is often not possible. So then there's no workaround, okay? But type 2 error is failing to reject H naught when it should be rejected. So usually due to small sample sizes, right? The sample wasn't large enough to detect the difference. I'll put that in brackets. The sample wasn't large enough to detect the difference. Okay. So the only way we can increase the sample size in an attempt to avoid type 2 errors. We can increase the sample size in an attempt to avoid type 2 errors. Okay. All right. So with only one example, I know that's not enough, but I'll give you guys some practice. Well, I'll give you an assignment to practice with. But what I want to do is get into chapter 6. Now, remember, 6.1 is basically just a recap of chapter 5. So that's the end of chapter 5. And now 6.1 is just a recap of chapter 5. Chapter 5 was like a long drawn out thing, and then we recap it again. And so here in chapter 6, that's when we start inference for categorical data. So 6.1 is called inference, inference for a single proportion. It's a recap of chapter 5. We introduced a one sample proportion question type. So here, the type is one sample proportion. So if you want to recap, then you can read all of chapter 6.1. But for us, what I want to do is just focus on the only new thing in 6.1, which is calculating sample sizes. So the only new thing in 6.1 is calculating sample sizes. Which is going to be that last formula on the formula sheet. This one here. Okay. But we're going to build it up. Okay, so you'll have it and it's there, but we're going to get there naturally. Okay. So what we want to do is, okay, so we need to decide some sample size. So before we conduct a study, we usually need to know, okay, roughly what sample size do I need, right? And then the follow-up question would be, well, need for what? And your response would be, well, for my margin of error to be less than 3%, right? 2%, 1%, that kind of thing. Okay, so it's all going to be based off of your margin of error. Okay? And so let's jot that down. So before we collect any data, we need to decide what sample size will help us achieve a predetermined margin of error. At some specified confidence level, right? Margin of error goes back to the confidence interval. And so before you even collect any data, you want to say, okay, in my report, I want to be able to report a 95% confidence interval, and I want the margin of error to be less than 5%, 3%, right? 0.03, for example, right? Then what does my sample size need to be able to do that? And then whether you can get that sample size or not, that's another issue, right? But at least you have an idea of what you need, okay? So predetermined margin of error at a specified confidence level. So if you recall from the confidence interval, right, p hat plus minus z star times the square root of p hat q hat over n. This chunk, that plus minus chunk buffer, whatever you want to call it, is the margin of error. So what I'm going to do is I'm going to let lowercase m denote the margin of error. Oops. So what I have then is I have m is z star times the square root of p hat q hat over n. So what I've said is, okay, I'm going to force my m to be some value, right? And if I fix my confidence level, so 95%, my z star would be 1.96, for example, right? So those two values, so these first two values are already predetermined, right? And then what I want to do is I want to solve for n, right? And so we need to solve for n. Solving for n, I get m is divided by z star. And you don't need to do this derivation. I just want to show you where it came from. And then you don't need that formula on your formula sheet. If you're okay deriving it every time, that's fine too. So this is going to be times the square root of p hat q hat over n. If I square this, oh, new page here. New page, who dis? Is going to be p hat q hat over n. Solving for n, right? I'm just going to do a quick switcheroo here. I'm going to multiply this over. I'm going to divide this over here. And so what I get is that n is going to be z star divided by n, right? Because when I switcheroo things over, still squared, but flipped around times p hat q hat. Right. Little switcheroo, but this is what's on your formula sheet. Right. So the problem is, well, I'm trying to figure out what sample size I need in order to be able to collect a sample, and then from that sample, I'll have some p hat. So a problem is I don't have p hat, right? And so there are two different options that we have. We can either use a previous, so if this is a yearly thing that you do, right? A yearly survey or whatever, then you're gonna have some idea of what the proportion is. Maybe use last year's proportion, right? But if you have no clue and you want to maximize the sample size that you would need, then you use 0.5, right? That's gonna, so a 50-50 split, p hat, q hat, 50-50 split is gonna give you the maximum value of n But then if you have some idea, then because it's expensive to collect a data set, right? And so then if you don't need to collect the maximum value, then you would rely on the previous proportion. Okay, so since we don't have p hat yet, we replace p hat and q hat in this formula with p star, q star, p star and q star. Oops. Option number 1 is going to be that p star is equal to 0.5, right? Which means that q star is also 1 minus 0.5, which is 0.5, right? This is if you have no prior knowledge about the population, right? No prior knowledge about the population. Okay. This produces the maximum value of n. So if you want a maximum, so the kind of the ceiling level of n, then use 0.5. If you want to save some money, and I know I'm running out of time here, I am out of time, use p hat from a previous study. P hat from a previous study. Right. Which means that q star is, of course, 1 minus p hat. Yeah. This will produce a slightly smaller value for n. This produces a smaller value of n, which is cheaper, which would be the reason to do it. And on that note, I've got an example for you guys. Maybe I'll put it in before I post the notes. It's going to be 6.15. I'll put it in and let's see here. And we'll start there on Thursday. Oh man, so much scrolling. But if you have any questions, let me know. Otherwise, I will see you on Thursday. Wow, so far. Okay. There. There. I'll end this recording here. Oops.